All right, we've got one more day of AP review, a couple more AP practice problems, and my focus today is looking at how they ask related rates questions. So both of these have little related rates in them. Number one says, cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. Can's initially empty, and rain enters the can during a 60-day period. The height of the water in the can is modeled by the function s, where s of t is measured in millimeters and t is measured in days for 0 to 60. The rate at which the height of the can of water is rising in the can is given by s prime. Okay, so sometimes I like to kind of draw out what I can. We've got a cylindrical can. Something like that. They tell us the radius is 10. And the other pertinent information is that the can's initially empty. That's important. The height of the water is s of t. So s of t equals height of water at time t. And then the rate at which the water is rising is given by s prime. So we don't know s, but we do know s prime. And s prime is 2 sine of 0.03t plus 1.5. Okay. Part A, according to the model, what is the height of the water in the can at the end of the 60-day period? So we want the height at 60 days. We want s of 60. Essentially, I know what the height is initially. I know s of 0 is 0. So if I want s of 60, but all I have is s prime and s of 0, what can I do? Hopefully you're thinking fundamental theorem. Good. So the integral from 0 to 60 of s prime of t, remember your dt's, they will take off for that, equals the height at 60 minus the height at 0. Okay, so then I can plug that in. Math 9, 0 to 60. And again, s prime is 2 sine of 0.03 x plus 1.5 dx. Make sure your mode is in radians. Oh, see, mine was in degrees. So I'm going to switch over to radians there. And then hit enter. 171.813 equals s of 60 minus 0, because we said s of 0 was 0. So they say indicate units. Nope. So you don't have to indicate units, but it is in millimeters. Okay, there's part A. Part B. According to the model, what is the average rate of change in the height of the water in the can over the 60-day period? Show the computations that lead to your answer. Indicate units of measure. So make sure you put units on this one. Now we want the average rate of change. Average rate of change is a fancy word for what? Slope. It's different than instantaneous rate of change. So average rate of change means I take s of 60 minus s of 0, change in y, over change in x, 60 minus 0. Now remember, some of you get confused when you see the word average. I don't have the instantaneous rate of change, or I don't have the rate of change as a formula. Average rate of change means slope. Okay, so this is just going to be 171.813 minus 0 all over 60 minus 0. So essentially, I'm just taking this answer that I had and dividing it by 60. 2.864. And the units on the y values are millimeters, and the units on x, I believe, are days. Yep, so millimeter per day. So over the course of those 60 days, that's essentially how much rain there is per day. It's a lot of rain. Okay, C. Assuming no evaporation occurs, so there's no water leaving the can, at what rate is the volume of the water and the height of the can changing at t equals 7? Indicate units of measure. So they ask for a rate of volume. That's kind of like a related rate. We want dV dt. When do we want it? Now, when t equals 7. So first I need an equation for volume. What's the volume of the water in this can? You gotta know volume of a cylinder. And volume of a cylinder is pi r squared h. Okay, now a couple things. Remember, you're allowed to plug in anything that's constant. Is there anything constant about this formula? Yeah, r. The radius of this can is always 10. So remember, things that are constant, we can plug in early. What's the height of the can? And this is a little tricky too. That's why I wrote this out. S of t is the height of the water. So that's changing by a formula that we don't technically know. So volume is equal to pi times 10 squared times S of t. In other words, volume is 100 pi times S of t. So if I want dV dt, 100 pi is just a constant. So it's a constant times a function. And the derivative of that is the constant times the derivative of the function. And it's already with respect to t. We want it specifically at t equals 7. So dV dt equals 100 pi times s prime of 7. Remember, s prime is 2 sine of 0.03, so I can just type that in. 2 sine of 0.03 times 7 plus 1.5 is that number times 100 pi, remember? So times 100 pi gets me 602.218. And they need units again. We're in volume. Since the height's in millimeters, the volume would be millimeters cubed. With respect to time, is still per day. Again, I would only put units if it asks for them. Okay, lastly, part D. During the same 60-day period, rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. The height of the water in the can on Monsoon Mountain is modeled by this function m, where m equals this crazy equation. The height m of t is measured in millimeters and t is measured in days, just like our other one. Between 0 and 60, let the function d of t equal m prime minus s prime. Apply the intermediate value theorem to the function d on the interval from 0 to 60 to justify that there exists a time between 0 and 60 in which the heights of the water in the two cans are changing at the same rate. Okay, let's break this down. The heights of the water in the cans are changing at the same rate. So the height of the water in the original can is S of t, and the height of the water in this new can at Monsoon Mountain is m of t. So if they're changing at the same rate, m prime is equal to s prime. So same rate implies that m prime equals s prime. But if m prime equals s prime, what's true about d? Well, if this is equal to that and you're subtracting them, d equals 0. So it implies that d of t equals 0. Okay, so in order to use the intermediate value theorem, what's the only condition that has to hold? Well, you just have to show that the function is continuous. It doesn't have to be differentiable even, but this one is. So continuous, this is a polynomial, so the derivative is going to be a polynomial also. So we have a polynomial minus a sine function, which are both continuous. So we can say since both m prime of t and d prime of t, oops, not d prime, sorry, s prime, are continuous, d of t, which equals m prime of t minus s prime of t, is also continuous. We need to look at the endpoints now. Remember, the intermediate value theorem says if you're continuous, then if you take your endpoints, every value between these endpoints has to be hit somewhere. I'm trying to prove that d of t equals 0 somewhere between 0 and 60. So hopefully, if I look at the endpoints, I have a number less than 0 and a number bigger than 0. Let's see. What's d of 0? Well, that would be m prime of 0 minus s prime of 0. So to find m prime of 0, all we have is m right now. So if I do math 8, the derivative of, oops, 1 over 400, here's alpha y equals, times 3 times 0, oops, I don't want to plug that in yet, 3x cubed minus 30x squared, but not in the exponent, sorry about all this, plus 330x. Evaluated x equals 0, so that's 0.825-ish. Minus, I got to plug 0 into the sine function also. So 2 sine of 0.03 times 0, so sine of 0 is 0, plus 1.5. We technically don't even need a calculator for this. I get 1.5. So if I take my 0.825 minus 1.5, I get negative 0.675. And then I gotta check the other endpoints. Now I want d of 60. So that would be m prime of 60 minus s prime of 60. All right, well, I'm going to use what's already been typed in. Let's go up here. Let's take that, but instead evaluate it at x equals 60. 72.825 minus s prime of 60, so 2 sine of 0.03 times 60 minus 1.5, 0.4476. And when I subtract those two, oops, wait a second, that was plus 1.5. Knew that sounded off. Okay. 60 plus 1.5 is 3.447. Oh, almost the same. Okay, good. So I can do 72.825 minus that number, and I get 69.377. Okay, so we've got a negative number and a positive number. So if I'm at negative 0.675 at 0, and at 60 I'm at 69, and I'm continuous, then somewhere it has to equal 0, which is what I was trying to show. So since d of t is continuous, and d of 0 is less than or equal to 0, which is less than or equal to d of 60 by intermediate value theorem, there is a time between 0 and 60 when d of t equals 0, which means there's a time when m prime equals s prime. And that's how you use the intermediate value theorem. Okay, so this question had a little bit with a related rate, not a big one, but a little weird spin on it. But then it also dealt with a lot of other calculus topics, and that's what these free response questions are going to do. They're going to take lots of different topics. All right, let's just do one more, and then we'll be done. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. The oil slick takes the form of a right circular cylinder with both its radius and height changing with time. And they give you the volume of a circular cylinder. Okay, let's talk about the pertinent information. It forms an oil slick whose volume is increasing at a constant rate of 2,000 cubic millimeters per minute. So we know that dV over dt, the change in volume, is 2,000. And I don't know if units are going to matter, but it's cubic millimeters per minute. It takes the form of a right circular cylinder. It'd probably be a pretty thin one because it's just oil. But the height and the radius are changing. And they give us that the volume is pi r squared h. Part A says at the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeter, the radius is increasing at the rate of 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time? So they're starting us right off with related rates. What do we want? We want the rate of change of the height of the oil slick with respect to time. So we want dh dt. And when do we want it? Now. We want it when the radius is 100 centimeters. We want it when the height is 0.5 centimeters. And the radius is increasing at a rate of 2.5 centimeters per minute. So dr over dt is 2.5 centimeters per minute. Okay, so we've got to use our volume equation, which is volume equals pi r squared h. And is anything constant? Can I plug in r and h? No, you can't. Both its radius and height are changing. If you can picture this oil slick, as it gets bigger and bigger, the height's getting bigger and the radius is getting bigger. It's changing in both directions. So if I'm going to take dV dt, what rule do I have to use? Product rule. Watch out for product rule on this test. So dV dt equals the first. I'm going to take pi r squared because pi is just a constant as the first, times derivative of the second, dh dt, plus the second, h, times the derivative of the first. If pi r squared is all one piece, the derivative is going to be 2 pi r dr dt. Okay, plug in what you know. Now you do know dV dt, that's why I write that information, 2,000. So 2,000 equals pi times r is 100, so 100 squared, times dh dt, which is what I'm looking for, plus h, which is 0.05, or 0.5, times 2 pi r, 2 pi times 100, times dr dt, which is 2.5. Okay, so I'm going to move all this to the other side. So 2,000 minus 0.5 times 2 pi times 100 times 2.5. So 2,000 minus all of that gets me 1214.601-ish. And that equals pi times 100 squared times dh dt. So I'm just going to divide by pi times 100 squared now. So I take that number divided by, in parentheses, pi times 100 squared. Make sure you put that in parentheses or use alpha y equals. And we have 0.039. And its height, so that's going to be heights in centimeters, centimeters per minute. Okay, so that's part A, classic related rates. And I just looked at it. This is cubic centimeters. I think I missed that up. That was centimeters. Still my last question was millimeters. Okay, part B. A recovery device arrives at the scene and begins removing oil. The rate at which oil is removed, R of T, is 400 radical T cubic centimeters per minute, where T is the time in minutes since the device began working. Oil continues to leak at a rate of 2,000 cubic centimeters per minute. Find the time T at which the oil slick reaches its maximum volume. Justify your answer. Okay, so this is one of those rates going in, rates going out questions. Let's make up, we don't really have an equation for volume. We have volume that it's growing at. We used V for that. So let's use another letter for the volume of the whole cylinder. It's the oil slick. So let's say the oil slick's volume. So O of T equals volume of oil slick and T is time since device began working. Okay. Now, we don't really have an equation for the volume. What we have is information about the rate that it's changing. It's leaking continuously at a rate of 2,000 cubic centimeters per minute. So that's the rate that it's increasing, and it's getting pumped out by this rate. So we have a rate of change of the volume right now. O prime of T is equal to the rate of it increasing, 2,000, minus the rate of it decreasing, which was R of T. Okay? So O prime of T essentially is 2,000 minus that R of T, which is 400 radical T. Okay, now what did they want? They wanted find the time T at which the oil leak reaches its maximum. So a max can happen at endpoints or critical points. Critical points would be where O prime is equal to 0. We can solve that pretty easily. 2,000 equals 400 radical T. Divide by 400. We'll get 5 equals radical T. Look, I didn't need my calculator. T is 25. So that's a critical point. Is it a maximum, though? Well, let's see. Put 25 on a number line. Pick a number before 25, like 1. If I plug in 1, 2,000 minus 400, that's positive. If I plug in a number bigger than 25, like 36 because it's a perfect square. Radical 36 is 6. 20 minus 2400 would be negative. So it's increasing always before it and decreasing afterwards. That is a max. And I don't really have to consider the endpoints because over at 0, if it's always increasing before and always decreasing after, because I don't know what an end time is, this is going to be the only max. It's got to be higher than it was at 0. It's got to be lower than it would be after 0. And it's got to be higher than it would be after 25. So max occurs. Let's see what it asked for. Find the time when the max occurred. So this is time, t. Max occurs at t equals 25 minutes. And it says to justify. Because the volume of the oil slick is always increasing before t equals 25 and always decreasing after t equals 25. And that's enough to justify. It's always increasing and always decreasing. We know we've got our max. Okay, last part. By the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. So essentially, if time is since the device began working, time 0 means that the volume was 60,000. Write but do not evaluate an expression involving an integral that gives the volume of the oil at the time found in part B. Okay. So we know that the oil at time 0, that's O of 0, is 60,000. I want the oil at time 25, and I have an equation for O prime. So how can I get O of 25? Fundamental theorem it is. Integral from 0 to 25, 0 because I know that was 60,000, is 2,000 minus 400 radical t. Don't forget your dt. That would equal the oil at 25 minus the oil at 0. And since I know this is 60,000, when I add that over, we're going to have that O of 25, the oil volume at time 25, is equal to 60,000 plus the integral from 0 to 25 of 2,000 minus 400 radical t dt. And I could easily get that answer, but it said write but do not evaluate. So there's the answer. All right, that's it. So there's a couple examples of how related rates could potentially show up. Notice fundamental theorems always there, along with other calculus topics also. All right, keep the studying up. You've got this. Good luck.